Hi, so I'm Toby Wiseman. I'm in the Theoretical Physics Group at Imperial College, and it's a pleasure to give a lecture, an hour and a half or so, on gravity and black holes and AdS as part of this London Theory Institute lecture. I'm assuming you are PhD students, and I'm assuming you're early year PhD students. Some of you may be working in gravitational areas, and some of what I say, therefore, may be rather simple. Others may be working in completely different areas. Hopefully, there'll be a mix of useful stuff for both variety of people. And in the problem sheets, there are some easier problems, which I hope, if you're not familiar with this stuff, gives you a sort of lead into it and some useful tools that you could apply in other situations. And if you are familiar, there's a couple of questions at the end that are a little bit harder. The last question is definitely a little bit tougher, and that should, be an interesting challenge. Good. So let me get on. I've got lots to tell you about. Let's talk firstly about motivation. And the motivation for thinking about AdS and asymptotic AdS spaces is really, in the modern context, AdS-CFT. Of course, people considered AdS before AdS-CFT came along, but really AdS-CFT has given us a huge motivation to think about it. The point about AdS-CFT, I'm sure you all know, is that certain d-dimensional CFTs are thought to be equivalent to gravity or some quantum gravity, maybe I should say, in asymptotic AdS in d+1 dimensions, at least d+1 dimensions. And by quantum gravity, this can be rather general. What I mean is space-time is dynamical. Whereas if on the left-hand side, this corresponds to CFT, it isn't. That's the key point. One of the reasons that the right-hand side has to have dynamical gravity in is because every CFT has a stress tensor, and the stress tensor on the right-hand side is associated to dynamics of a graviton, some sort of graviton. So it may not look like an Einstein theory of gravity, it may be some very complicated higher spin theory, but nonetheless, space-time should be dynamical, we think. The CFT lives on the boundary. We can think of it as living on the boundary of the AdS, and it's got some number of degrees of freedom. So I should say this side here, we have a negative cosmological constant, say lambda, and obviously there's also a Newton constant here, g, from gravity. Over here we have some number of degrees of freedom, which is sort of measured by something called the effective central charge. I'm not really going to talk about CFTs in 2 dimensions. This is the central charge. In higher dimensions, it's a coefficient that enters into the 2-point function, the stress tensor. And there is a relation between all of these quantities. Over here, the cosmological constant, as we'll see, we can write as 1 over a length scale squared. That length scale we call the AdS length scale. And the relation is that the Newton constant, this length scale, can be related to the effective number of degrees of freedom, the central charge of your theory. And therefore, in order to have a weakly curved gravity, this should be large. So this is large for weak curvature. Otherwise, it's a highly quantum theory of gravity. In n equals 4 Super-Yang-Mills, this is something you can calculate very explicitly, and it's something like the rank of the gauge group. Let's say for a UN gauge group, this is a curly n here. It's something like n over, 8 pi squared. So roughly speaking, the number of degrees of freedom squared is related to the ratio of AdS to Planck length. That motivates us to understand this side of the correspondence, because this correspondence tells us the dynamics here is the same as the dynamics here. And if we want to understand strongly coupled CFT, typically gauge theory dynamics, we can think about it, at least when we've got many degrees of freedom, in terms of a gravitational problem, albeit living in this peculiar asymptotics. And that's really the key motivation. So things I want to describe today as a sort of plan for the talk. Let me give you a rough plan for where we're going. I'm going to tell you what AdS is, because it's a funny old space. AdS we can think of as the vacuum state on the right-hand side. It plays the role of the vacuum state on the right-hand side. So if you put the CFT in the vacuum, if you like, the gravity is sitting in AdS. If you excite the CFT, the gravity theory will be some excitation about AdS. We'll then talk about other geometries. Let's say asymptotic AdS geometries, and I'll give you some examples, like some black holes. These, as I say, will be non-vacuum states, thermal states or excited states. The CFT lives on the boundary, and we'll talk about what the boundary of an AdS space is, but in particular we'll also talk about the stress tensor of the CFT. The expectation value of the stress tensor of the CFT is related to the gravitational stress tensor in AdS. And we'll see that because AdS acts a bit like a box, it's got a boundary, there's a stress tensor we can define there, and in particular that will allow us to define energy in the gravitational theory. So we'll talk about that, the boundary stress tensor. We'll talk a little bit about the properties of black holes. And I'm going to talk a little bit about Euclidean methods to calculate properties of black holes. And if you've seen this, then great, you can skip that. But if you haven't seen it, Euclidean methods are a very interesting and subtle way of doing all sorts of black hole calculations. They're very neat. And you'll have some practice in the example sheet doing that. And then we'll talk about the path integral. Or partition function in the Euclidean context of the gravity theory, which is supposed to be equal to that of the CFT theory. And I'll explain how to calculate that. Okay, so that's a sort of plan for the talk. Let's get going. Oopsie. Right, so what is AdS? Let's talk about that first. So D plus one dimensional AdS, I can embed as a hypersurface. So embed as a hypersurface. Like this. In a double sort of Minkowskian flat spacetime, so a two-time spacetime like this, I can embed this hyperboloid into this double-time Minkowski. And that is what's called the universal, or that rather is when you take the universal cover, AdS space. So this has closed time-like curves. So this has closed time-like curves in it, and therefore we pass to the universal cover. Oh, how do I spell universal? Universal cover, and that's what AdS spacetime is. And it's often nice to think about this embedding. In particular, some of the symmetries become very easy to see. In particular, there's an SO2, let me get this right. What is the symmetry? It's an SO2D symmetry, which is actually the CFT in D-dimension symmetry group, and that's not a coincidence. But you can understand this symmetry just arising from the usual Lorentz symmetry of with two times of this two-time Minkowski space, which obviously preserves this, which we can think of as a sort of a vector in that space. which has got some norm L squared. And we call L is the AdS length. Now, to actually put coordinates on this in a useful way, we can take the global chart where we take coordinates like so. We take U, V like this. This is very similar to how one might embed just a sphere in and we've got some angular coordinates. I'll just call them omega I. These would be things like sine theta, cos theta, sine phi, cos theta, sine cos phi, and so on, the usual way. So in particular, this is a unit sphere, coordinates on a unit sphere. And if you embed like this, plug this into this hypersurface equation, you'll get the induced metric on AdS, which in global coordinates can be written in this form. So this is a d-1 sphere, I think. And we can often, it's often written in the following way with a slight change of coordinate. So it's written in this sort of Schwarzschild-like form, but this function f differs. So if f was just 1, this would be flat space, and what you see is that f grows away from the origin of this space, and that's what gives you this different asymptotics. Here, note that r is L sinh rho, to go from one to the other. In particular here, this is a nice set of coordinates. It completely covers this hyperboloid, and in particular, we've passed to the universal cover. Tau is not an angle here. Moving to the universal cover precisely means unwrapping these closed time-like curves and taking tau, practically speaking, it means taking tau not to be an angle, which would give us closed time-like curves, but to take it to be r. Okay, so in a sense, it wraps over this hyperboloid infinitely many times. In this form, we don't see the full SO2D isometry. We see an SO2 cross SOD isometry. Clearly, we've got the sphere SOD. But really, if one thinks in this form, the SO2D, which acts in a nice linear way on these coordinates, just as a sort of double time Lorentz matrix, acts in a very complicated way, in a nonlinear way on these coordinates. But nonetheless, one could work out the details if you had to. Okay, so what about the asymptotics of this space? Clearly, compared to flat space, this looks rather different because of this term. So this is a space that we can what's called conformally compactify. Okay, and it's a conformally compact space. So if we have a space like this, which we can write like this, so we can write it in terms of a metric g tilde and a function z, which lives over, which is some function of these coordinates x. This is called a defining function. And if z goes to 0 on a hypersurface, and also we need the condition that dz doesn't vanish, so it's not got a vanishing gradient there, then z equals 0 is a conformal boundary. Okay, so it's a conformal boundary of the space. And you can think about this in all sorts of contexts, but in particular, AdS is of that type. Now, let us just change coordinates. In fact, let me just see what I've got written here. Oh, I should also say that the boundary geometry, so this isn't a real boundary. So the boundary, or the conformal boundary geometry, is equal to the boundary geometry of G tilde. Okay, so where Z goes to 0 here, clearly this space basically blows up into some asymptotic region, typically. But at this place where Z goes to 0 on this hypersurface, I should have emphasized, this is a perfectly regular metric, nothing funny going on. So this thing at the place where this function goes to 0 on some hypersurface, we can just regard that as a boundary of this. This is a real boundary, and there's some induced metric on the boundary. That induced metric on the boundary of this is what we call the conformal boundary geometry. And note, it's only defined up to a Weil rescaling, because of course, if you write the metric in this way, I can redefine a new defining function, which is some smooth function multiplying this function that goes to 0, and then I get some different defining function, and that will rescale this by my smooth non-zero function, and that will give me a different boundary metric, which will differ by precisely some smooth function multiplying it, which is a Weil rescaling. Okay, so conformal boundary isn't a real boundary, it's a different thing, but it's something we can define up to Weil rescaling. Now let's take e to the rho equals 1 over z in our previous metric, and then asymptotically, well, and then we have as z goes to 0, the metric that we wrote down previously goes to this. So if we take this thing here, when rho becomes large, these become exponentials that are growing, and that's where z is going to 0 here. And so we can see that z equals 0 here. This is a perfectly regular metric at z is 0. And so we see that the boundary, we can regard this as 1 over our defining function. And then that tells us that the boundary metric, let's call it dsB, the conformal boundary, I should say. It's the conformal boundary. It's the real boundary of this, but the conformal boundary of the full space is this thing, which is the Einstein static universe. So time cross a sphere. Okay. Note a space-like curve. Is infinite length to the conformal boundary. If you try and, I mean, it's a simple exercise, just integrate from some non-zero z to z is 0. Because of that blowing up factor, you get an infinite length. But interestingly, a null curve, and again, you can do this, a null curve has a finite affine length. Finally, I just want to say, and that's important because what it means is that short wavelength modes of some dynamical fields reach the boundary, this conformal boundary, in a finite time. They can really, we can picture this boundary as a sort of wall, and then if I've got some physics happening here and some stuff going out, maybe a massless field, it will hit the conformal boundary in a finite affine time and bounce off it. And so we can think of ADS is like a box. even though the wall of the box is an infinite space-like distance, it's a finite null distance, and that's what really counts in terms of dynamical field. And in particular, it means we have to put some boundary conditions there. There's another chart called the Poincare ADS chart. And in that chart, one finds this form of the metric. And you can again figure out how this embeds in the hyperboloid. I won't write it down. The formulae are slightly messy, but there's an embedding, but it only covers half of the hyperboloid. And so, in fact, in the full unwrapped universal cover, it covers a sort of wedge. So in particular, our picture, note here, by the way, though, the conformal boundary of this part of ADS is basically Minkowski, because already this is the defining function, and this is then the regular space, and this is the boundary of the space, just this part here. Okay, so we can picture ADS as a sort of solid cylinder going on forever. In this global chart, we saw that the boundary, the conformal boundary, I'm probably just going to call it a boundary from now on, is time across the sphere. So here's the sphere, time is running up, and then in the interior, the space is sort of filled in by this ADS geometry. And this Poincare chart, if you like, covers something like, if I take null slices, oh, that didn't quite work. If I take null slices, where they intersect here, they sort of carve out a wedge. This would be the Poincare chart. It just covers that wedge. But this cylinder goes on forever. What else did I want to say? We have these symmetries. We have this SO 2D symmetry. In the Poincare chart, we can easily see, let's just go back to it. I won't even write it down. It's obvious that under a Lorentz transformation of the x coordinates, this is invariant. And therefore, I can think of this Lorentz transformation of the x coordinates generating a diffeomorphism of the bulk, which is an isometry, a killing symmetry. It leaves the metric invariant. And indeed, on the boundary, it just acts as a Lorentz transformation. Okay, so we can see, we have a sort of, in fact, we can do it with the full Poincare group, of course. Poincare isometry, well, we see, let's say, part of the isometry group leads to a Poincare symmetry transformation on the conformal boundary. In the Poincare chart, we can see that in the Poincare chart easily. But if we go back to also in the Poincare chart, we can see that if we take z goes to lambda z, x mu goes to lambda x mu. So this one, of course, was just x goes to a mu plus some Lorentz matrix like this, and z goes to z. But we also can see that this metric here, if I scale the x's and the z's, because of this factor here, it's again invariant. So we have another isometry. This is another isometry in the bulk, which generates a dilatation symmetry transformation on the boundary. Okay, why does it generate a symmetry? Because on the boundary z is 0, the action is just this, which is of course exactly a dilatation. And in fact, so there's also the other symmetry parts of the conformal group. And so in fact, the SO2D isometry acts on the boundary as the conformal group. So it's not just the case that this is the conformal group in D dimensions. The isometry transformations in the bulk, the vector fields that generate the isometries, if we restrict that action to the conformal boundary, they actually generate the symmetry transformation of the conformal group on the boundary. Very good. Okay, and that's why that's the link to CFTs. Let me also just say it's an Einstein space, meaning that the Ricci tensor is proportional to the metric. In fact, the Riemann tensor can also be written just in terms of the metric. So it's a negatively curved Einstein space. By the way, I should have said I'm using the conventions of Wald in terms of signs of curvature tensors and so on, and also my metric signature is the usual GR1 minus plus plus plus. So this tells us this would be a negatively curved space. And so we can also regard AdS as a solution of the Einstein equation with a negative cosmological constant. Okay, so that's AdS. That's the first part of this talk, and then we'll talk about asymptotically AdS spaces and some of their properties.